Welcome to this extended ONPAR task training video for the end of unit assessment in Water and Landforms. In this video, we will summarize the key science ideas, practices, and cross-cutting concepts assessed in this task, present focal content, unique functionality, and scoring on each interactive screen, and look at the type of information that can be found on the individual and the classroom score reports for this task. This presentation is an extended version of the training video found in the teacher portal for Where's Water Task 4. If you're looking for a shorter overview of standards and screens, click Training in the resource menu associated with this task. An overview of key science ideas, practices, and cross-cutting concepts assessed in this task can be found in the teacher guide. To find this information for any task, click on the associated teacher guide. The end-of-unit assessment for any task covers content and practices from the previous two interactive tasks and sometimes includes a question related to a paper task. In this case, assessments are limited to the content in Task 1 and Task 2. Looking at the overview diagram, you'll see that the content covers all previously covered, with emphasis on continual cycling of water and uneven distribution of water resources. Continual cycling of water is the main concept assessed in Task 1, that's the water cycle, and uneven distribution of water resources, including groundwater, is the main idea assessed in Task 2. Modeling is the main practice that's being assessed in this task. However, as with all ONPAR tasks, students will need to employ more than one science and engineering practice as they work through the screens. And cause and effect is the main cross-cutting concept. Next, we'll discuss each screen in the task, but before we do that, let's download an answer key. To find answer keys for any task, navigate to Interpreting Scores in the teacher guide and click on the answer key. A PDF document will open up in a separate window for you, starting with the scoring rubric, which shows an overview of how partial and full credit are awarded on each interactive screen, followed by an explanation of each correct answer for each screen in the task. All right. To exit the teacher's guide, we're just going to use the back arrow on our browser, and then we'll scroll down and click on Preview Full Task for Task 4 to see each screen. And here we are on Screen 1. And as always, the first screen in an ONPAR task sets the scene for the entire assessment. And so this one asks the question, how does Earth's water move into and out of lakes? Check here in the lower left-hand corner to see how long this task is, and it is 9 screens long, and we're, of course, on Screen 1. The navigation bar indicates that this is simply a still picture. There's no animation to view, so we click the only blue tool that's available to move forward. Screen 2 is a model. It should look a little familiar to you. There's a very similar looking model on Task 2, Screen 9 of Task 2. Let's see what this one has to say. Model the amount and motion of water on a sunny day in 3 locations. So the locations, instead of being 3 locations underground as with the previous model, this one is 3 locations as you're looking at the cross-section of a lake. So the area above the surface of the water, which is the water table, the water itself, and in the land below the water. Okay, and we have controls that are also similar to that Task 2 model. Everything starts off in the off position. All of the sliders are off. And in order to see anything, you have to turn all of the sliders on. Now, in this case, this question doesn't tell the students to turn all sliders on to see anything. So they would have worked on a model previous to this, but you may need to remind them to turn on all the sliders so they can see the water molecules. And if you may remember, the last one had the amount of water molecules and the arrangement. Those were the two things that we could compare. In this case, we've got the amount or number of water molecules that will give students an opportunity to compare the volume of water in these three regions. But instead of arrangement, we have motion. And that's because we also want to have the students tell us something about the phase of water that they expect to be in these locations. And so above the water table, we would want them to show us that this, in fact, is largely water vapor. And so the water vapor should be moving around more quickly than the liquid water. And that's an additional piece that is different from the model on task 2 and comes from the ideas that were assessed in task 1, the idea of evaporation. All right, well, let's play with this model and see what we have. I've already turned on a bunch of water molecules. Let's get them moving a little bit faster. In fact, let's go all the way to the top. So now I've got my water molecules moving around pretty quickly above the water, expecting there to not be as much water in the air as there is in the water. That's kind of an odd way to say it, but let's dial back on the number here a little bit. Let's see. Well, there should be some water vapor, so I'm going to set it to this point where I have just a few water molecules bouncing around there above the surface of the water. In the lake, here's our liquid water. Now here would be, I would say, probably the most water. So let's make sure that we've got the highest concentration of water molecules in our water. Let's check out the model, and it goes from most down to least. So let's set that one to most to have the highest density there in our pure water. And the motion, well, we want it to be slower than the speed of the water molecules moving around. Let's see what other options we have. We have this slow speed, this middle speed. Hard to tell. It appears pretty similar to that above, and then the highest speed of all. Definitely don't want that high speed. Let's keep it here for now. Okay, let's go on to the bottom layer. Now this bottom layer, the sediments here, is intended to be a mixture of soil and impermeable rock. So just like the model on task 2, these darker areas are supposed to be places where we would not want students to put water molecules, because those are sections of rock that water can't enter. So I actually have a pretty decent looking arrangement right now, but for some reason the molecules aren't moving at all. That doesn't quite make much sense. Let's see what other options we have for the motion. So we have stopped, moving a little bit, spreading all through. So we've got sort of a combination. This motion on the lower level is kind of a combination of arrangement and speed. So we definitely don't want it running all through this material. So this is not a good choice, nor is that. This is not a good choice because it's completely stopped, and we want to have some motion. So I guess that leaves us with the middle setting. And for number, let's take a look at those now. We've got this same density as setting as in the lake, and that doesn't feel quite right. There's a lot less space here, and definitely there's going to be some soil material, some actual molecules of soil material, so less water below the solid of the lake. And so let's see what other options we have. In the middle, not very much at all, and nothing. So I'm quite sure that the middle setting is intended to be this, just not enough water, given that this soil would be saturated down here, and there are definitely places where there's no water molecules at all. It doesn't make a lot of sense for this model. So this, I believe, is the fully correct answer. Let's check it out in the rubric. And this is kind of hard to hold in your mind, but in fact, these are the settings that we just talked through, with the least number of water molecules moving around very quickly in the air, the most water molecules in the water and then moving around in the medium speed, and then using that same speed, because we're still talking about liquid water, but having the number fill in the areas where it's supposed to be soil, but not cover up the areas where it's supposed to be impermeable rock. So this is the model that we're looking for as the correct answer on screen 2. And then if we scroll up to see how the scoring is done, how the points are awarded, we see that it's by location. So all 3 locations correct is 3 points, 2 locations correct is 2 points, and one of those 3 locations correct is 1 point. Okay, so let's go on to screen 3. So this screen should look a little familiar. This is the exact same screen that students would have interacted with on task 1. It was screen 2 of task 1. So let's see what it has to say. Read the data and predict the water level in the lake for January through April. Now, what we're really asking here with these predictions is for students to show us their conceptual understanding of precipitation and evaporation, 2 really important processes and concepts in the water cycle, and show us that they can apply those ideas to a real-world situation, which is the lake level. And so we've got the data for the 4 months, and we have the starting water level. And so we're going to start at 500, and then in January, we had 8 centimeters of precipitation and 12 centimeters of evaporation. So more evaporation than precipitation. That means that our lake would have gone down by 4. So if we just start them at 500 so that they're even and go down to 496 is the correct answer for January. Taking a look at February, they're balanced. No change in water level in the month of February, so we'll set those to be that same, 496. In March, again, we've got this pattern of more evaporation than precipitation, and the difference is again 4 centimeters. So now we have to go down another 4. So let's go down 2 and 4. So now we're down to 492. And then in April, got a lot of rain in April, looks like. So we have 20 centimeters of precipitation, only 12 centimeters of evaporation, and that would bring the water level in this lake back up to the original, 500. So this would be a correct answer. This is one of those cases where there really is only one correct answer. But let's take a look at the answer key, because it's also the case where if a student made a simple subtraction error over here in January, it would follow through to the rest. So it wouldn't be totally fair from a conceptual point of view to look at each one of these in isolation. Student could have made a early math error and then everything else would be wrong, but maybe they have the right idea. So we'll check the rubric to see how that's handled, and we're on screen 3. So here it says that for 3 points, the pattern of increases and decreases from month to month is consistent with the data for all 4 months, and water level predictions are accurate. Okay, so we've got accurate water level predictions and the patterns are right. For 2 points, the pattern of increases and decreases from month to month is consistent with the data for all 4 months. However, the levels are not accurate. So that's however the levels are not accurate. That's where we account for the math or one math error. So if they make a math error in the beginning or the middle, but they've got that kind of general pattern of starting high and then going down in the middle, they'll still receive 2 points, even if most of their numbers are actually wrong. For 1 point, the pattern of increases and decreases from month to month is consistent with the data for 2 of January and February, February and March, and April. So they're at least showing us decreases in the right place and increases in the right place, even if they're just totally messed up by the scale. And that's what we're trying to get at 1 point. They have some conceptual understanding of precipitation and evaporation, but for some reason the graphs are throwing them off. That would earn them 1 point. And anything more incorrect than that is 0 points. All right, and just going down to be complete, you can see here is the way what the answer key looks like. It tells you the answers and also the patterns. And by the way, I'm just noticing this now. Apologies. This is in millimeters here, but the screen was converted to centimeters for students to make it a little bit easier. So this is actually, these are the same numbers. Okay. All right. So let's go on to screen 4. Screen 4 should also look familiar. This is from task 2, and it was part of a 3-screen erosion series. In this case, in the end of unit, you'll find as we go forward that this is the only screen about erosion. We don't go on to ask the kids to explain, and that happens sometimes in the end of unit assessments where there's a longer series in the first task where the kids see the question the first time, and then sometimes the question is asked in isolation a little bit on the end of unit. So that's one of these cases, and it asks us to order the risk of erosion for the features around the lake. So here's our different, if you remember from the last version, our different slopes and our different amount of plant coverings. We did add rock coverings here, so a slightly different concept, but still something added to the landscape to help limit erosion. And we're asking students to select the least risk of erosion and then order from least to most. So we're looking steep slope with nothing to hold the soil in place for the most. The next one, gentle slope, but still nothing to hold the soil in place. The third answer, number 3 on this list, is a steep slope with rocks. And then we go in order by slope with these 3 plant. Oh, I've got them in the wrong order. Here we go. These 3 with plants by slope. So steep to less steep to completely level with plants. This is the correct answer for this particular screen, and in this case, it's the only correct answer as well. So let's go down, I'll show you the only correct answer. We did have some discussion, some teachers ask about the rocks, but it turns out that something holding the soil in place rather than nothing sort of overpowers or trumps the slope. So with the rocks in place, you can have soil held on a steeper angle than if there's nothing at all. All right, then we go up to the scoring for screen 4, and all 6 correct in a row as you just saw it for 3 points. For 2 points, at least 4 ground types correctly ordered. And so that looks at the entire set of 6 and looks for 4 things that are in the correct order, even if 2 are reversed. For example, could be the middle 4, could be the one and or the other, or could be 2 and 2 or 1 and 3, as long as they're in the right order. And for 1 point, the first least and the last most is correct. So the 2 outside extremes are correct, or first 2 and the last 2 are correct. So they understand enough about risk of erosion or how to prevent erosion that they can get 2 in a row on those ends. That's what earns 1 point. Anything other than that, and students will earn a 0. Okay. Let's go on to screen 5. Screen 5 is a context screen. This is similar to screen 10 of task 2, where students are given a map of water around the world. So this is a water distribution question series. Read the data about Earth's lakes. And this is also a little bit interactive. So you can see there's an on-off button here. And what this does is this just turns different data points on and off. So if students were interested in only looking at the lakes in the red zone, the location of the lakes in the red zone, and the relative amount of, in this case, water loss, then they could turn off the blues, or they can keep all of the data on. So this information is here. To figure out what we're asking about it, you need to move forward. Okay, so this is a kind of a dense screen, similar to the last screen on task 2. Compare water volume in North America's lakes. Explain your answer. So Here are the same controls I just talked about, make it just in a small version. Water volume in North America's lakes is, and we're looking for changing. Now notice this has an autofill. This is a little bit different than the functionality of the previous version of this type of question. So if you select changing, it fills in changing automatically. If you select stays the same, it puts stays the same. So again, it sort of frames your answer and helps students. If they get to the end and it doesn't make sense, then they need to take a look at the claim that they make. So the best answer here is changing, because we see that there's a lot of increasing and a lot of decreasing going on. For example, lake here, as with the prior version of this question, you can pick any lake. We're going to pick Lake A. Lake A is located in this spot, and it is in the red, and it's decreasing quite a bit, so is decreasing. And now to make our claim, let's pick one that's increasing. So we want to pick a blue. Let's do C. C is increasing. So now we've got some nice strong evidence for our claim of change. And now because, what would change the amount of water volume in these lakes? What would lead to that? And so here are our choices. Precipitation would lead to that. Temperature would lead to that. Recharge would lead to that. Tides, no, doesn't really affect the lake levels. Gravity, nope, not so much. Human activity, would human activity affect lake levels? Sure, I suppose if the ground around it was changed, so we'll put that one in. So here's our 4 possible reasons for the lake levels to be changing. And let's take a look at the answer key and see how close we came. We'll scroll down to screen 6, and we're looking for changing. We're looking for an example of decreasing and an example of increasing from the data. And here are our 4 reasons. Temperature, precipitation, human activity, and recharge are changing. Going back up and looking for screen 6 at the way the scoring was done. This is again a 3-point screen. Comparison and explanation are correct. So they've filled in all the boxes correctly. For 2 points, 2 of these are correct. The water volume pattern, the top line, 2 examples with trends, the middle line, and the reasons, the bottom line. So they have 2 of the 3 lines completely correct. The third line could have 1 or more mistakes. And then for 1 point, 1 of those 3 lines is correct. So this is also a similar scoring scheme to the similar question on task 2. All right, so let's move back out, and we'll go on to screen 7. So this screen is actually a combination of screens from task 1 and task 2. The task 1 version of the screen asks students to model the water cycle, actually 2 ways that water moves through the environment, which is exactly the same as the instructions here, show 2 ways that water moves through the environment. Except in that case, there was the drawing was a little more traditional. It didn't show as much of the underground environment, although there were some spots underground. So the task 2 version that this is combined with shows many more of these underground locations. In either case, we want students to start and end at the same location. So that's indicating that we're looking for a full cycle, and that some dots may not be used. So there are a lot of different possible ways to answer this question. And so many of these dots, depending upon what you draw, may not be used, but there are 3 dots on the screen that would be incorrect in any case. So these 2 dots that are surrounded by the gray, and this diagram is just like the one on screen 2, where we want students to assume that this gray is impermeable rock, and so no water is going to be getting to these locations. And then the third dot that is not correct in this model is the inside of the confined aquifer. Now, certainly if we drilled a well and we got down into this aquifer, we could draw the water up. But naturally, it would be very difficult once water made it down into this location for it to enter into the water cycle. Water stays down in some of these completely confined aquifers for hundreds, maybe thousands, possibly more years. So those 3 spots are not correct, but all of the other spots are included in one or more cycles that would be considered correct answers on this screen. So we've got 2 colors of arrow, a black arrow and a red arrow. We want students to show 2 complete cycles. And so let's begin with the black arrow. In both cases, for a fully correct cycle, we would like the cycle to run through this rain cloud right here. This is representing our precipitation. So running through the rain cloud and heading down towards the Earth because of gravity is one requirement for a correct answer. And then students need to complete a pathway that makes sense. So here we've got the rain falling, and then it's either entering the stream and flowing downhill, or it's running off on the surface and running downhill, seeping into the ground, continuing to move underground, but down towards the center of the Earth because of gravity. And then in this case, this dot, because it's half in the water and half out, that's meant to represent exchange of water between the larger lake or ocean here and the underground. And so this water can get out and could make its way up into the air. So some evaporation could take place. So let's show that. And back up into the cloud where the water vapor condenses, and there we've got one possible complete cycle. It doesn't need to be this elaborate. It doesn't need to employ as many spots. Another possible correct cycle would again include this rain cloud, but it's possible that the rain falls a little bit farther down the mountain, maybe continues in this stream over the surface, falls into this lake, evaporates, and then ends up back in the cloud. Here's another possible cycle. So there are at least 75 different combinations that are considered correct. So instead of drawing more, let's take a look at the diagram that's provided on the answer key. And you'll see, here you go. Now these colors are not significant. It's just to make it a little bit easier for you to see all the arrows that are crossing. So notice the atmosphere is an important place for a lot of these cycles. This location of the atmosphere was not part of the prior model. So this might be a tricky one for some kids. And here are those 3 spots that I talked about that are not part of any correct answer. And here's that location, the one place on the map where we're allowing, actually there's 2 places where we're allowing some upward flow. Okay. All right. So let's go up to the scoring itself, the numerical scoring, to see how this works. So for 3 points, this is the 3-point column, 2 correct cycles with no extra arrows. So that's a perfect answer. Lots of different combinations, but they end up with 2 and they don't put extra stuff on the screen. 1 correct cycle could have some extra things, is on the screen is 2 points. So 3 points, perfect. 2 points, they've got 1 good cycle in there. The other one is incorrect or missing. And then for 1 point, students have at least 1 closed pathway. So they're showing a cycle of some kind that includes the rain cloud and at least 1 other liquid reservoir. So, but they could have errors elsewhere. So they have something that includes the rain cloud and 1 other spot, but they've made some mistakes. So that's the scoring for screen 7. Let's go back. And by the way, I know these arrows look a little thick. This was done on purpose for if you have students who are using tablets, the thinner arrows are difficult to erase, especially when they overlap. So in order to remove an arrow on the screen, you need to use the eraser, and it just gives them a little more space to click on the arrow. Okay, Let's go forward. So now this screen should also look familiar. It's got these pins that you drop into spots. We've got the same diagram in the background. We did include some slightly different locations. We have our atmosphere, we have the leaves of our tree, but we also have this cloud over here to the right-hand part of the screen. And we're looking for students to label how and where water moves with the red pins and identify the driving force or energy for how water moves with a blue pin. Use all the pins. Some dots may not be used. So each of these pins has to be placed somewhere. And as with the prior versions of this screen, in some cases there's more than one place that would be correct, but students need to place each pin somewhere. And we've got two different kinds of information. We've got these processes and these definitions of locations underground that are represented by the red. And then we've got the forces or the driving forces or energy represented by the blue. So let's just start placing some pins. Condensation, a good place for condensation would be up here in the cloud. Evaporation, any surface, any place on the surface would be a good spot for evaporation. Transpiration, really this tree leaves is the only place where students can label on this graph. They can label transpiration on this graph. Surface runoff, this is a good spot. Recharge zone, various different answers would be correct here, but let's use this place up here in the mountains where we're recharging the water. It's a source of water for the underground environment. Saturated, we know below the water table, and again, this black line represents the water table. This area is saturated. Aquifer could be here, but is also a confined aquifer. This would be fine. Now we're looking for places where gravity is involved in moving the water through the water cycle. Light energy is involved in moving the water through the water cycle, and thermal energy. So gravity, lots of possibilities here. Let's go with my favorite in the mountain spot for gravity. Light energy. The tree leaves is a good place for this because light is involved in the process of transpiration, but there are others that are acceptable. And thermal energy, well, there's a lot of thermal energy released when the water changes phase. So this is a good spot. Thermal energy also is involved in the process of evaporation on the surface. Another good spot. There are several. All right, so this is one possible correct answer, but let's take a look at that scoring guide to see the other possibilities. Roll down here to the diagram, and there you go. There you go. You can see lots of different possible correct answers. Okay, now we'll go up on screen 8 and see what the scoring scheme is like. And to the rubric. Okay, so this is a 4-point screen. This is the 4-point column. And so at least 9 labels are correctly placed for 4 points. 7 or 8 labels correctly placed for 3, 5 or 6 for 2, 3 or 4 for 1. So 2, 1, or 0 correct pins earns students 0 points. But there are actually 10 pins to place on this screen. So 9 or 10 correct would earn students 4 points on this screen. Recognizing that there's just a lot of information that students need to consolidate and bring together in order to get all of the correct pins on this screen. So we allow them one error and they still earn full credit. All right, so let's go on to the last screen. Water moves from place to place on Earth. What 2 things are true about how water moves? So this is looking back at task 1, where there was a theme. If you read the teacher guide, you noticed it, or you paid attention to some of the answers that were in the some of the statement frames there. Gravity and sunlight are the 2 major factors that move the water cycle. Gravity pulls water down towards the center of the Earth, and sunlight contains the thermal energy that allows the water to change phase and to complete the cycle. So these are the two answers that we're looking, or the two options that we're looking for students to talk about. One statement about gravity and one statement about sunlight. So gravity, something. What does gravity do? It either pushes, pulls, shapes, or cycles. And gravity pulls is the best answer there. So gravity pulls water. Where does it pull it? Towards the core, Earth's surface, the sun, the moon. This is the answer that we're looking for here, towards Earth's core. For the sunlight statement, sunlight, what does sunlight do? Does it push, does it shape, or does it cycle? This is maybe a little bit of hesitation here on the right answer, but what we're looking for is cycles. So the sunlight allows that cycling by, again, enabling the phase change. Sunlight cycles water on our surface, to the sun, to the moon. And we're looking for on Earth's surface, the idea that the sunlight, the influence of the sunlight, has to take place above the surface, at the surface or above it. It's not a factor underground. All right, so those are the two correct statements. And in this case, those are the only two correct statements that students can make. There's not another possible combination, so we won't go down to the correct answer key, but we will take a look at how the partial credit is awarded. So both statements have to be correct for 2 points. This is just a 2-point screen, notice. So both correct for 2. For 1 point, either students get one statement fully correct, or they get both yellow responses and a green response correct. So let's go back and look at the screen. So both of these yellows, the gravity and the sunlight, those are those two key ideas that by the end of this unit, students really should understand that those are the two major factors in the water cycle. And then one of these greens has to be right. So pulls is perhaps the easiest one, but who knows? So 2 of these and one green would also earn students a point. Okay, so now we are at the end. We're on screen 9 of 9, and we also know it's the last screen because the check mark has become blue. It's become active. So let's click on that. Students always have to say yes. They have to confirm that they're interested in ending it, because this is where, when they click on yes, their score report pops up. In the preview, that doesn't happen, but we still need to exit the preview. So this actually takes you back to the planning page within the teacher portal. And then the next step, because that doesn't score, let's take a look at 2 score reports. So let's take a look at one of these test classrooms. So I've opened up the top test classroom and I see all the controls. Let's close a few of these windows so they don't become confusing. And we'll scroll down and we'll open up the unit that we're interested in, which is Water and Landforms. And then we'll scroll back up. Here's our list of students in this test class, and let's bring up their results for Water and Landforms. And the first thing we'll do is just take a quick look to see if everyone has completed the task. And as a matter of fact, everyone has. We see the green check mark with the graph next to it. That means that the task was submitted. If you see a yellow check mark, that means that the task was started but not completed, and NA means that the task was not started. So you can take a quick look to see if students have completed their work, and everybody here has. So we seem to be in pretty good shape. Let's take a look at one of those individual student reports. This is Jacob's results. Congratulations, Jacob. On the top of every student report, you can see how that student did on each screen compared to the total number of points available on each screen. Looks like Jacob still had a little trouble with the risk of erosion. So the erosion content, and showing 2 ways, that's the water cycle modeling, got 0 points on those. But the rest of the screens, he was able to collect some points, and on the last screen, he collected full credit. So decent job. Let's scroll down and see if we can get some more information. Under the science ideas, you did not correctly identify this. These are descriptions of the types of errors that were made on the screens. Screen 2, screen 4, screen 6, screen 7, screen 8. And so this kind of information is most useful on a debrief. Say you're going through the entire task with your students after everyone has taken it, doing a debrief, looking at a screen. Students can take a look at the individual feedback on their reports, and they can get some general information about where they might have gone wrong. And so that's where this information is most useful. They may not understand and may incorrectly think. These are statements that are based on evidence that is generally collected across multiple screens. And so in this case, Jacob's responses led us to believe that he may not understand how to interpret and model data about Earth's water and how water moves and concentrates in areas above and below Earth's surface. And so this might be tied to that water cycle screen with a 0, plus maybe some answers on other screens, how to interpret and model the data about Earth's water. That could be related to maybe a not perfect score on screen 6. And again, probably more than one screen feeding into that piece of information. And then it seems Jacob may incorrectly think that water cycles along pathways that it doesn't. So that kind of indicates that this 0 on the water cycle screen, it's not because the screen was skipped, and it's not because cycles weren't made. Cycles were made, but it's just that they were totally incorrect. And so another piece of feedback under there, labels we may use to describe where water can be found are interchangeable. So Jacob may incorrectly think that, and that is most closely related to that screen with the pins. And so Jacob did pretty well on that screen, 3 out of 4, but there may be a few key errors that triggered that statement. And then again, some feedback on other screens. And then also may incorrectly think factors that cause more erosion cause less erosion. So that has to do with that erosion screen and assessing the risk of erosion from least to most. And you can see how Jacob did not do well at all on that one. So actually may have some ideas completely reversed. So that's Jacob's feedback about the science ideas on this assessment. And then if you scroll down, you can see the feedback for the modeling, the practice of modeling. And there are 3 categories here. There are a lot of modeling screens on this task. And so the designers thought it was worthwhile to give students separate information about each one of the screens. And they fall into different categories. So on screen 3 and screen 8, Jacob did pretty well with modeling, demonstrated an ability. On screen 2, demonstrated a partial ability. So there were some errors there that suggested an issue with modeling on screen 2. And then screen 6 and 7 did not demonstrate an ability. Those are the most problematic as it relates to modeling. And then if we look at the bottom, green section here, cross-cutting concepts. Our cross-cutting concept is cause and effect. And based on Jacob's answers, it looks like he was able to demonstrate a partial understanding of cause and effect. Perhaps a little more work to do there, but seems like he's on his way. So that's a typical individual report. Now let's take a look at the report for the entire classroom. So to do that, we scroll over here into the control area and click on the icon under reports for task 4. Comes up looking pretty similar to the student report, except these numbers actually indicate a distribution of students and tell you how many students received each score point. So if you're interested to find out who got the perfect scores on screen 2, you can click on this number and it'll list their names, and you can always click through to look at their individual reports. And you can do that for any one of these score points. You can also look for general patterns yourself and see where there was a concentration of zeros or where students did well, or a split result like this, where you have students that really get it and another set of students that really don't. So this kind of thing, having to do with the erosion content, for example, you might want to think about how you're gonna tackle the struggles that these students are having while allowing these other students, giving them an opportunity to perhaps go on or deepen their understanding because they got the basics based on this question. And then as we scroll down to the bottom of the report, you can see here are those may not understand and may incorrectly think statements. These are all of them that anybody in the class received, with the accompanying percentage of students who received that statement. And if you click on any of these lists, it tells you who's in that group. So I just clicked on some students may incorrectly think water on Earth is distributed equally. Here are 3 students who were unable to read the data on those lake maps and see an unequal distribution of water. So for these, you can handle this really any way you'd like, but one way to do it is to look for extremes. 76% is the highest percentage, and this has to do with students incorrectly thinking that labels we use to describe where water can be found are interchangeable or not specific. So it was that labeling screen. Students seem to have a lot of trouble there, and this might even indicate that that they just put pins anywhere. So whether this is an issue with the question and persistence or the content, you may want to dive into that and maybe have students try it again, because there was quite a bit of trouble in this group on that screen. Some ideas that don't warrant going back to. Gravity's force on Earth's water is different based on location. That doesn't seem to be a problem for this group. Only one student, only Jordan, made some errors on that idea. And then here's another one: water distribution decreases when data suggests otherwise. So here are things that students didn't have trouble with, only one each. So if you're differentiating, and you may want, if this were the same student, you may want to try to find them some special help. But in fact, this is 2 separate students. So using this information to group students together so that they can help each other with some peer work, or taking small groups of students to work on a concept while the rest work on something else. This kind of information can help you with that differentiation, with that grouping. One more comment about the percentages that you see here. This looks a little funny that this is all 71%. And this kind of thing where you get a lot of the same percentage points, this happens more with these test classes that we created, because we purposely went through and tried to get students scoring in every score point category. So it's not exactly, it doesn't really represent reality. But the other thing to note is that these are not all the same students. Many of them are the same, but each list is slightly different. So when you see the same percentage, don't assume that it's the same kids. Take a look, click through, take a look at the names, and then use that information as you would. The last way that you can use this information, because this is the end of unit assessment, compare it to the goals of your curriculum. And if there's an idea here that is not important to your curriculum, then there's really nothing more to do. But if the idea has a high percentage and it's something that either is in your curriculum or is something that your curriculum is moving towards because you're working towards the NGSS, then you may want to add more emphasis in next year and beyond. So, and then we scroll down and we can take a look at the science and engineering practices. And this, again, this is all the screens. And you can just take a quick look and see the percentages of students who did well on screens, had a little trouble, but were able to demonstrate some ability on screens, and those screens where students had trouble. And looking for extremes here, again, is probably a good idea. 59% of the kids could not demonstrate an ability to model on screen 6. So then you may want to go back to screen 6, take a look at the skills that are needed there, and then do more problems like that with your students in the future, even as you go on to different topics, different content areas. And finally, cross-cutting concepts. Cause and effect is our cross-cutting concept. You can see the 4 categories. Now, it's not exactly, but these percentages tend to mirror total points. So in general, these students are the ones who also scored the most points as a whole on the assessment. And in this category, this weak evidence of understanding, these are the students who would have scored the lowest in general. It's not exactly always the case, because cause and effect may not have come into play on every single screen, but these distributions, when it's presented this way, tend to give you an idea of how your students did overall, from best to worst in terms of points. All right, so that is Water and Landforms, end of unit, and we hope you found this useful.